In this video, we're going to be talking about the node voltage method, also known as node analysis. So to begin, we need to go over a bit of terminology so we know what we're talking about here. So first of all, we have a node, which is a point where two or more circuit elements join. Then we have an essential node, which is a node where three or more circuit elements join. And then we have a branch that's a path that connects two nodes. If you take a look at the circuit below, you'll notice that it has three essential nodes where three or more circuit elements join. You have one here, and one here. You may think that there is four, including this spot here. However, if you were to redraw the center of this circuit, you would have R3 here, R1 here, and R2 here. And actually that node at the bottom is those two nodes are the same node. So that's going to be our third essential node. So now that we have our three essential nodes, we know that there will be n-1 equations needed to describe this circuit. So since we have three essential nodes, we're going to need two equations. The next step is to select one of the three essential nodes as a reference node. Though the choice for the reference node is arbitrary, it usually makes the most sense to choose the node with the most branches. As we can see here, the node on the bottom has the most branches, and we determined that these 2 points are indeed the same node, so we're just going to select this as our reference node. After selecting the reference node, we define the node voltages on the circuit diagram. First of all, a node voltage is defined as the voltage rise from the reference node to a non-reference node. So as you can see, we have the voltage rise to we'll call VA, and the voltage rise from the reference node to VB. We can denote this as plus and minus, and we'll label this VA right here. And we have also plus, and the minus will come over here, and VB. Using Kirchhoff's current law, you're going to take the voltage drop of the current away from the node in question. So if we start with VA, the current away from VA is going to be VA minus V1, which is 10, divided by 1, which is R4. The current in the next branch, leaving VA, is going to be VA minus 0, which is our reference voltage, over 5. This is why it makes sense to place the reference voltage where we did, because it makes it easier to simplify. We know VA minus 0 over 5. You can just write this in the future just as VA over 5. The last branch, leaving VA, we're going to have VA minus VB over 2, and this is all equal to 0. This concludes our first equation, and we have one more to go. So our second equation, we're going to have the current leaving VB, which is going to be VB minus VA over 2 plus VB minus 0 over 10. And then we're going to subtract the current, which is 2. Since we don't have a voltage here, we just have the current. This is all equal to 0. Notice we use negative, because if you're doing the voltage drop away, the current is going the opposite way. It's going on the voltage rise. Therefore, you're going to have negative current. Now that we have our two equations, we can solve for VA and VB, and you'll find that VA is going to equal 100 over 11 or 9.09 volts. And VB is going to equal 120 over 11, or 10.91 volts. You can solve these by hand or plug them into your calculator as solving a system of equations. Let's take a look at another example. We're going to have a few currents drawn in. First, we're going to start off by identifying our essential nodes. We know that we have one node here, and we know that this node is going to be the same as the other node, just like we did before. And then we're going to know we have another essential node right here, and we know this is the same as this node, just like we did before. There's only two essential nodes, therefore we're going to have NE, which is 2, minus 1. We're going to have one equation to solve this circuit. So first we start off by identifying one of our essential nodes as a reference node. We can choose this one right at the bottom, just like we did before. Then we can name our essential node VA, and then we can solve the circuit. So we're going to take the current away from the node VA minus V1, which is 50, divided by 5, plus VA over R1, which is 10, plus VA over R2, which is 40, since we said those two nodes at the top were technically the same node. And then finally, we're going to have minus 3 for the current, because how we said before, the convention here, the current is going opposite of our voltage drop, therefore it's negative. This is all going to be equal to 0. Since we only have one equation, you solve for VA. Because I like to take shortcuts, I'm going to type this into my calculator, and the answer that it gives me is VA is going to equal to 40 volts. In this example, we're also going to find the current, and since the current direction was also already given to us, we can start off doing Ohm's law the correct way. So we're going to do IA is going to be equal to V1, which is 50, minus VA, which is 40, divided by 5, which is going to equal to 2 amps. IB, following the same direction, you're going to have VA, which is 40, minus 0, which is our reference, over 10, which is equal to 4 amps. And finally, we'll have IC is going to equal to VA, which is 40, minus 0, our ground, divided by 40 ohms, which is going to equal to 1 amp. Next, we can do some calculations about power. So, say we want to know the power associated with the 50 volt source. So we have the power of the 50 volt source is going to be equal to negative 50 times IA, which is going to be equal to negative 50 times 2 is equal to negative 100 watts. We use negative 50 in this convention because IA is traveling on the voltage rise of V1. Therefore, we use a negative convention here. Say we want to find the power associated with the 3 amp source. We know that P is equal to the current times the voltage. And we know, like we said before, the current is going on the voltage rise, not with the voltage drop. Therefore, you're going to have a negative convention. you're going to put P is equal to -3 times the voltage, which is 40 volts for VA, which equals -120 watts. Checking our answers, we can use P equals I squared R. And for IA, we have 2 amps. 2 squared is 4, so 4 times the resistor 5 is going to equal 20. And then for IB, we're going to have 4 squared is 16 times R1, which is 10. You're going to have 160. And then finally, we'll have IC, which is 1. 1 squared is just 1 times 40 is equal to 40. If you add these all together, you're going to get 220 watts. Which balances out the equation, noting the total power delivered is 220 watts, and this is the total power absorbed by the 3 resistors. The next example, we're going to be doing nodal analysis, but with dependent sources. First, you can notice that there's 3 essential nodes, so we're just going to name them. We have V1 and V2, and then our third node we're going to indicate as the reference node. So right off the bat, you're going to see that you're going to need 3 minus 1 equals 2 equations to solve this circuit. So our first equation, away from V1, we're going to have V1 minus 20 over 2 plus V1 over 20 plus V1 minus V2 over 5. It's going to be equal to 0. And then our second equation is going to be V2 minus V1 over 5 plus V2 over 10 plus, now we have our dependent source, which is V2 minus, so as you can see here, 8I naught is actually just a voltage, so we're going to have minus 8I naught over 5 is going to be equal to 0. So to eliminate the variable I naught from the dependent source, we need to express the controlling current in terms of the node voltages. So we're going to have a third equation here where I naught is going to equal V1 minus V2 over 5 as denoted here. Again, the fastest way for me is to type these into my calculator as a system of equations, and you get V1 is equal to 16 volts and V2 is equal to 10 volts. Solve for I naught. Using the convention, we're going to do V1 minus V2 over 5, which is going to be equal to 16 minus 10, which is 6 volts, over 5 is equal to 1.2 amps. If you wanted to know the power dissipated by the 5 ohm resistor, take the current across that resistor, which is going to be I naught, which equals 1.2 amps. So we're going to have P equals I squared R, which is equal to 1.2 squared times R, which is 5. And this is for the 5 ohm resistor, which is equal to 1.44 times 5, which is equal to 7.2 watts dissipated. Note by the positive convention. A good exercise to build your problem-solving skills would be to switch the reference node with V2 or V1 and try to solve it that way. You'll find that it might make it a bit harder. Either way, it's good practice. This concludes our video on nodal analysis. Be sure to check our next video about supernodes when a voltage source is connected between two essential nodes.